Good afternoon. We are continuing with synchronous motor drives further. In the last few classes, we had looked at hunting oscillations, then V and inverted V curves of the synchronous motor after deriving the power angle relationship for a cylindrical pole synchronous motor. So today we are going to look at mainly 5 things if time permits. The first thing we are going to look at is the salient pole rotor configuration. We'll derive the power angle relationship. And after deriving that, we will look at reluctance rotor and permanent magnet rotor synchronous motor as a special case, as special cases. Then we will go back to discussing starting a little bit, especially what happens due to the influence of permanent magnet or how exactly the damper bar behaves during starting. And after that, we will look at dynamic braking of a synchronous motor. Then we will go over to the variable frequency operation. Particularly, we will be looking at true synchronous mode of operation. So as far as the salient pole motor goes, we had already said that the salient pole rotor actually will have protruding poles, or the poles would look clearly distinct. So let us say if this is going to be my synchronous motor's cross section of the stator, then I will have A dash, B dash, and C dash as the three-phase windings. So let me write them. A dash, this is B dash, and this is going to be C and C dash. So these are going to be the three-phase windings. Now, as far as the rotor is concerned, we are going to have, in the case of salient pole rotor, I'm going to have the rotor pole somewhat like this. This is how the rotor poles are going to look like if I'm talking about a two-pole configuration. And let's say this is North Pole and this is South Pole. And along the axis of the pole, we call this as a D-axis. So along the D-axis, we are going to have very, very minimal air gap, whereas along the Q-axis, we are going to have a larger air gap. So whenever a winding is aligned along with the pole, that is along the D-axis, the inductance manifested by the winding is going to be quite high. So XD is going to be quite high. If I'm calling this as synchronous reactance along the direct axis, this will be quite high. Whereas when the same winding occupies the space along the Q axis, if I try to look at what is the kind of inductance value it is manifesting, if I call this as XQS, that is synchronous reactance along the quadrature axis, that is going to be smaller as compared to direct axis reactance. So the drop that we consider in the winding along the direct axis and quadrature axis, they are going to be different. So it's not very easy to depict this or represent this in an equivalent circuit. So we are going to look at it from the point of view of drawing a phasor diagram. So if I say that the direct axis is actually the magnetic field axis, and because we say d phi divided by dt is the induced EMF E, the flux or the magnetic axis and this E, they will be always at 90 degrees to each other. So if I am drawing, let us say E somewhat like this. Let me first of all draw the voltage E, which is the excitation voltage like this. So if this is E, this happens to be the quadrature axis if I am talking about this being perpendicular to the flux. And flux is always along the direct axis. So my direct axis has to be somewhere here. This is the direct axis. So E and direct axis are always at quadrature to each other. That's what I'm trying to get at. Now, if I take that maybe my armature current is somewhere here, this is what is my armature current. I'm showing this as stator current IS. If it is somewhere here, I can divide that along the direct axis and the quadrature axis. So I'm decomposing that current along direct axis and quadrature axis, and I'm calling this as IQS, and I'm calling this as IDS. And when I add these two, the summation of these two, vectorial addition of these two gives me the stator current. Now, whenever I'm talking about the winding occupying the direct axis position, it is going to have a voltage drop which has to be calculated by multiplying IDS with XDS. And similarly, whenever I'm talking about the winding occupying the quadrature axis position, I have to multiply this XQS with IQS, and then I have to add that as the voltage drop in the quadrature axis inductance. Now, IDS times XDS, because it is a reactance drop, it has to be leading IDS by 90 degrees. So I should have IDS times XDS somewhat occupying a position like this. So this will be IDS times XDS. Whereas IQS times XQS, if I try to draw, it should be at 90 degrees leading position as compared to IQS itself. So this will be IQS times XQS. This is how it should be. So let me draw these clearly. So I can say this is what is, let me probably erase this and let me write this E also here. Now I can write IDS times XDS along this. So this is IDS XDS. Whereas I'm going to have IQS, XQS somewhat like this. So let me draw this IQS, XQS somewhat like this. Now, when I add these three, that is E is added to IDS, XDS and IQS, XQS, then I should be getting what is the applied voltage or the armature voltage or stator per phase voltage. So let me draw this as Vs, which is the stator per phase voltage. Now, between Vs and E, whatever is the angle, that is what we called as load angle. So let me draw this as delta, which is the load angle. Okay, so I am drawing this as the load angle. Now, I can say that Vs cos delta. If I try to write what is Vs cos delta, that is actually from O until this P. This is going to be Vs cos delta. And that is equal to E plus IDS XDS. From the diagram, I can directly say this. And similarly, if I say this is PQ, which is actually the, if I talk about OPQ as the right angle triangle, PQ is the opposite edge. So PQ is going to be equal to Vs sine delta. That is equal to IQS XQS. From the diagram, I can directly say this. So from here, I should be able to write from this particular equation what I have written. I can write Vs cos delta minus E divided by XDS will give me IDS. Similarly, I can say from the next equation what I have got here, Vs sine delta divided by XQS, that will be equal to IQS. Okay, so these two equations give directly the value of direct axis component of stator current and quadrature axis component of stator current. Now, let me try to write the power expression clearly, like what we wrote earlier, the power supplied by the synchronous motor can be written as 3Vs Is cos phi. If I may call the power factor angle as phi. And here, if you look at it, this is the power factor angle because this is actually the angle between Vs and Is. So this happens to be the power factor angle. So if I want Is cos phi, I have to directly drop a perpendicular from Is to Vs. This is 90 degrees. So I should be able to call this as Is cos phi. This is what is Is cos phi. So let me first of all try to get Is cos phi in terms of IDS and IQS. So this is Is cos phi. If I look at this, this is IQS. So I should be able to again drop a perpendicular from IQS and that essentially comes up like this. So this is, let me just redraw this again. So this is Vs. Okay, this is Vs. So if I try to drop a perpendicular from here to from IQS to this, so this is the perpendicular that I'm dropping. We already dropped the perpendicular from IS to VS. So this particular length, whatever I am talking about from here to here, this entire thing is actually IS and this is IQS cos delta. So IQS cos delta is given, let me probably write this is OR and this is OS. So OR happens to be IQS cos delta and OS happens to be IS cos phi. And similarly, from IDS, I should be able to drop a perpendicular to the extended portion of VS. So if I drop a perpendicular here, this will be the perpendicular I'm dropping from IDS. So this length, whatever I'm talking about, this will be exactly same as if I had drawn an IDS would have actually come here. This would have been IDS2. So from here, if I drop the perpendicular, this particular length, that is SR, happens to be IDS sine delta. So this is actually delta. So this will be IDS sine delta. So let me first of all write here Is cos phi, which is equal to OS, that will be equal to OR minus SR. You look at this diagram, this entire thing is OR, that is IQS cos delta, and SR is IDS sine delta. So I can write OS equal to IQS cos delta minus IDS sine delta. Now we said power is 3 times Vs Is cos phi. So let me write power equal to 3 times Vs multiplied by IQS cos delta minus IDS sine delta. Now, if I say IDS is given by this equation and IQS is given by this equation, I'm going to substitute IDS here. Similarly, I'm going to substitute that IQS here. So let me write that this is equal to 3Vs multiplied by IQS is Vs sine delta divided by XQS multiplied by cos delta, and IDS is VS cos delta minus E divided by XDS multiplied by sine delta. Now, we can write this as 3VS square sine delta cos delta divided by XQS. And here again, this is Vs cos delta sine delta divided by XDS. So I can again say sine delta cos delta divided by XDS. So this is one portion. And the second portion is going to be minus multiplied by minus is plus and 3Vs and E. So I should be able to write 3Vs E divided by XDS sine delta. So this is the power expression. Let me rewrite this once again. I can write this as 3Vs square. Sine delta cos delta is sine 2 delta divided by 2. And I can write this as 1 divided by XQS minus 1 over XDS. And this portion is 3BSE divided by XDS sine delta. So this particular portion is very similar to what we had got in cylindrical rotor machine. So this is due to the interaction between the applied voltage and the excitation voltage. They are synchronizing with each other and we call this as synchronous power. Whereas in this particular portion, you don't have the field excitation at all. It is essentially due to the difference between the direct axis and quadrature axis reactances. So whenever the machine is running, the magnet is going to try to align itself in such a way that it is dragged along by the revolving magnetic field. The revolving magnetic field will be created because of the three-phase current carried by the three-phase space distributed winding. So we are going to have the revolving magnetic field rotating in the anti-clockwise direction like this for ABC phase sequence of supply voltage. So this north pole will be dragged along by the south pole of the revolving magnetic field and the south pole will be dragged along by the north pole of the revolving magnetic field. So that is because of the protruding nature of the magnet, field magnet. So this is essentially to minimize the reluctance. So we call this as the reluctance power. So there are two portions of power in three-phase salient pole synchronous machine. One portion of the power is called reluctance power. The other portion of the power is called synchronous power. Synchronous power is present in both cylindrical machine as well as salient pole machine. It is actually because of the interaction between the applied voltage and the field excitation EMF, whereas the reluctance power will exist even if the field excitation is absent. It is because the magnetic poles in the rotor, which are salient in nature, they want to align themselves. They will be dragged along by the stator side revolving magnetic field. So this is generally known as reluctance power, which will be absent in the case of a cylindrical rotor machine. So if we are talking about a salient pole machine, we have to take into account both these portions, reluctance power as well as synchronous power. As an approximation in some of the salient pole machines, if the reluctance power is really not dominating, if the difference between XQS and XDS is not much, in that case, we are going to neglect that. We will approximate the analysis only by calculating the synchronous power like what we do in the case of a cylindrical pole machine. So if we are talking about reluctance rotor, where the excitation is completely absent, that is the rotor will neither have windings nor have permanent magnet. So if both are absent, only reluctance power will be present. Only reluctance power will be present. So in that case, the excitation being absent, the entire flux production comes only from the stator side. So in one sense, it is like an induction motor where the magnetizing current is also drawn from the stator side. So in this particular case, what is going to happen is a three-phase revolving magnetic field will be produced because of the three-phase windings carrying their normal three-phase current, time-displaced current. So this is the revolving magnetic field. We are going to have North Pole and South Pole probably created like this. Now, as far as the rotor is concerned, we are going to have actually the rotor just, like a piece of iron it is going to be. So we will have probably this piece of iron being dragged along by this particular revolving magnetic field created by the stator currents. So this essentially makes minimizing the reluctance. That is the sole objective of this particular machine. So maximizing the flux or minimizing the reluctance, that is the reason we call this as reluctance motor or reluctance rotor. This particular structure we call as reluctance rotor. And because the magnetic flux is created from the stator side itself, the stator winding will always carry a lagging power factor current. The machine can never have leading power factor. It will always carry a lagging power factor current. So in this reluctance machine, only this portion of the torque, the reluctance power or reluctance torque only will be present. This portion will be absent. We will not have synchronous power at all. On the other hand, if we are looking at a permanent magnet motor, so the permanent magnet motor, like what we said in the first lecture on synchronous machine, it can be either surface mounted or it can be an interior permanent magnet machine. So in surface mounted case, what we are going to see is somewhat like this. If this is going to be my stator structure, and let us say this is actually my rotor, and I am going to mount the permanent magnet on the surface like this. So this is going to be the North Pole and this is going to be the South. So these are going to be the two magnets that are mounted on the surface. And nature is quite strange. This permanent magnet actually is the source of flux. But if you look at the internal reluctance offered by this permanent magnet, the reluctance offered by the permanent magnet material is equal to generally the reluctance of air or the permeability. If I try to look at it, the permeability of air will be same as that of the permeability of this permanent magnet. So if I'm going to have the windings here, this is A phase, and this is going to be B phase, and this is going to be C phase winding. If I try to look at what is the kind of reluctance offered along quadrature axis or direct axis, it is going to be exactly one and the same, because the permanent magnet material's reluctance is same as that of the air's reluctance. So here XD and XQ will be one and the same in the case of surface mounted permanent magnet machine. So this will behave very, very similar to a cylindrical pole rotor. The surface mounted permanent magnet machine will not behave any differently as compared to the cylindrical pole machine. Whereas if I am looking at the interior permanent magnet machine, if I am looking at the interior permanent magnet machine, if I say that this is going to be the stator cross section, I am going to have this as, let us say, the rotor, and I'm going to have the magnet buried here. This is going to be the magnet that is buried inside the rotor. So if I am calling this as the north pole, this is going to be the south pole. And this is the direct axis, whereas this is going to be the quadrature axis. And along the direct axis, because these magnets are embedded, the magnet generally is going to have very, very high reluctance, very similar to that of air. Whereas I'm going to have actually here, this is all iron. These are going to be iron. And iron is going to offer really low reluctance. So in interior permanent magnet machine, along the Q axis, there is iron, and along the D axis, there is permanent magnet, because of which D axis reluctance is going to be greater than Q-axis reluctance. Or in this particular case, I should say D-axis inductance. If I try to look at it, that is going to be smaller because the reluctance is higher compared to XQS. So it is exactly the reverse of what we saw in the case of a salient pole synchronous machine. We said that XDS is greater than XQS in the case of a salient pole synchronous machine, whereas it is exactly going to be the other way around in the case of an interior permanent magnet machine. And in an interior permanent magnet machine, because we have again two components of torque, one is going to be the reluctance torque and the other one is going to be the synchronous torque, just like what we saw here. And look at this, what we have as the reluctance torque, we said 1 divided by XQS minus 1 divided by XDS. That is what we derived as the expression. And in the case of salient pole machine, because XQS was smaller, the reluctance torque was positive in the case of salient pole machine. Whereas in the case of interior permanent magnet machine, this reluctance torque will come out to be negative whenever we are talking about the interior permanent magnet machine. So this will have a lot of implications in the performance of the machine, and especially when we talk about very high speed operation in the case of interior permanent magnet machine, which is commonly used in electric vehicles, we will be able to get a good amount of reluctance torque adding to the original synchronous torque, and then in a field weakening zone or high speed zone, this works out to be a big advantage for interior permanent magnet machine. So for today's class, I had said the first one I wanted to derive was the salient pole rotors power angle relationship, which we derived. And if I want to really draw, uh, uh, if this is the synchronous torque, how with respect to delta, how our power or torque is changing. The other one that is actually in 2 delta. So I will have the reluctance torque varying somewhat like this. So this red color thing is reluctance torque for a salient pole machine, whereas the green color curve, what I have shown, is the synchronous torque. Because the reluctance torque is a function of 2 delta, whereas you can see that this is 2 delta, whereas the synchronous torque is a function of just delta. So that's what we have shown here. So reluctance torque is red, and this green color curve that I have shown is synchronous torque. So we had seen the special case of reluctance torque and reluctance rotor and permanent magnet rotor functioning also. Now, let me just touch upon how the starting performance influence of field flux on starting. If you may recall, when we spoke about starting performance a few classes ago, I said that generally field is short-circuited during starting. Starting using damper bars. So if you may recall, what we said was that if we are going to have this as our stator structure, and I'm having the three-phase winding sitting here. I'm going to have the rotor somewhat like this. I may have the field windings sitting here, maybe the North Pole and South Pole field windings sitting here. On the other hand, I may have some damper bars sitting here along this. So these are damper bars, whereas these are going to be field windings, whereas these are the three-phase windings we talked about, A dash, B, B dash, and C, C dash. So the damper bars are extremely similar to, so if I talk about this as the rotor, inner rotor structure, I may have one bar here, second bar here, third bar here. Similarly, one bar here, second bar here, third bar here. So they will go along the periphery, outer periphery of the rotor like this. And these are going to be short-circuited somewhat like this. So this is essentially the damper structure. So when we are talking about the damper being used for starting, they behave extremely similar to squirrel cage rotor bars. And this squirrel cage rotor bar, generally, they are going to have induced EMF in any speed. When rotor speed is less than synchronous speed, this damper will have induced current. And because they are short-circuited, the current is going to circulate within the damper bar, and there will be interaction between the damper current and the stator side current or stator side revolving magnetic field, which produces induction torque. So the induction torque for starting is going to be produced by interaction between stator magnetic field and damper current. And once this induction torque is produced, immediately you are going to see that this starts rotating in the same direction as that of revolving magnetic field, very similar to induction motor action. And the speed will go pretty close to synchronous speed, but it cannot reach synchronous speed. The moment it reaches, if at all it reaches synchronous speed, then there will not be any induced EMF in the damper, and there will not be any induced current in the damper. So the induction torque will become zero. So always the speed will be slightly less than synchronous speed. And we said that at that point, when the speed almost reaches close to synchronous speed, the field short circuit will be removed, and we will connect the north pole and south pole current, or the DC current, to the field winding. The field structure will be fed with the field current or the DC current. And when we are actually connecting the field supply to the originally short circuited field winding, which has been now open circuited, and it is connected to the field supply, it has to ensure that if I am going to have the revolving magnetic fields north pole here and south pole here, then the rotor's field should be switched on in such a way that the south pole is somewhere close here and the north pole is somewhere close to the south pole of the revolving magnetic field, so that they are pulled in. So pulling in mechanism will be successful. What we mean by pulling in is the locking up of the stator and rotor poles. So if the stator and rotor poles have to be locked up properly, if it has to be pulled in properly, then the way the field supply is turned on, that has to be done very carefully, very judiciously, so that there is no repulsion, there is no slipping of poles of the rotor from the stator, and they actually work together with each other properly. They lock together with each other. So first thing is we have to ensure that sufficient amount of induction torque is developed. Second thing what we need to ensure is pulling in happens properly by switching on the field supply at an appropriate instant. To develop sufficient amount of induction torque, we had already studied in the induction motor, the induction torque, what is generated, will be proportional to the resistance, the rotor resistance. So if I have a good amount of resistance in the damper bar, so if damper bars have higher resistance, then I'm going to have a good amount of starting torque or the induction torque. So we might like to design the damper bar with higher resistance whenever we want actually the synchronous motor to start with a good amount of initial induction torque. But if the damper bars have a large resistance, let me recall the characteristics of the induction motor. This is how we drew the characteristics of the induction motor. So this is the torque, and this is the torque, and this is the speed. We drew the torque along the x-axis, and this was the speed. So this is the speed. So this speed is the synchronous speed. This is going to be the synchronous speed. So whenever you have the rotor running at synchronous speed, there is no induction torque at all. There will be only synchronous torque, provided I turn on the field supply. Whereas if I am talking about loading the motor a little bit, obviously immediately the speed is going to fall slightly. When the speed falls slightly, I am going to have this amount of torque generated as the induction torque by the damper bar. And whenever there is induction torque, immediately the machine is going to go towards synchronous speed. So it is going to travel towards synchronous speed. So it is going to travel in this direction. It is going to travel towards synchronous speed. How much is the induction torque developed? How much is the torque that is developed by induction action to push back the rotor to synchronous speed? That depends heavily upon what is the value of damper bar resistance. If I'm going to have the damper bar resistance to be larger, then I will have a characteristic somewhat like this. As the resistance increases further and further, I will have the characteristic somewhat like this. And whenever the speed is going to be different from the synchronous speed, you can see as the rotor resistance increases, damper bar resistance increases, this is all is the torque. This is the induction torque that is generated. Whereas if the resistance is somewhat smaller, I'm going to have larger and larger torque generated for the same amount of speed. If I'm talking about a particular speed, this is the speed, I will have much lower torque generated here. This torque generated is much lower as compared to what is the kind of torque generated at this point. So, in general, we would like to have a higher damper bar resistance if we want a better starting performance, but we would like to have a lower damper bar resistance if we want to have a good amount of damping performance. We don't want to have much of oscillations in the synchronous motor during load changes or during frequency changes. If we don't want to have good amount of oscillation, we want to have less amount of oscillation right away, the rotor getting back to synchronous speed, then we should have lower resistance. So starting performance is better for higher damper resistance, whereas damping performance is better for lower damper resistance. So we always have to hit at a compromise to arrive at some kind of via media so that both starting performance and damping performance is somewhat acceptable. Similarly, if we are having a permanent magnet motor, which is already having the magnet, in place. You cannot turn off the field. You cannot short circuit the field in that permanent magnet machine. So in permanent magnet machine, field is always on. Even during starting, field is going to be on. You cannot switch it off. If field is on, what will happen is in stator winding, apart from 50 hertz current, there will be other frequency currents also flowing. So if the speed is, let us say, instead of 1500 RPM, it is right now it is starting. So it is only 100 RPM or 200 RPM. We will have other frequency currents which are corresponding to 100 or 200 RPM. If it is 300 RPM, whatever we get as the frequency of the current will be 10 hertz. If it is 1500 RPM, it is 50 hertz current. So if it is 300 RPM, it is going to be 10 hertz current. So there will be multiple frequency component currents that will be flowing in the stator circuit, because of which we will have harmonic torques or subharmonic torques. So due to different frequency currents flowing in the permanent magnet synchronous motor during starting. Flowing in the stator. What we mean is in the stator, there are going to be stator winding, there is going to be multiple frequency induced EMF, and that is going to cause various frequencies, something like 10 hertz, 20 hertz, and 50 hertz, and all of them are going to flow. So we will have several frequency components of torque. So if we say that 50 hertz component, what we see is a steady value. We are going to have a steady value like this. Rest of other 10 hertz and so on, we are going to have, at a oscillation, which is actually corresponding to 10 hertz, 20 hertz, and so on, due to which you are going to see these perform like braking torque. So the performance of a permanent magnet synchronous motor should be in such a manner during starting that the braking torque has to be much smaller than the steady torque what we get as the starting torque. So the steady torque, T steady, has to be much, much higher than T braking. So it has to be designed in such a way that this happens properly so that it is able to start properly. So these are certain things that we need to take care when we talk about permanent magnet synchronous motor being started. Similarly, induction start, synchronous run motors being started properly with the help of damper bars. Okay. So the next thing that we are going to look at is braking action in a synchronous motor. We already said that a synchronous motor will run at synchronous speed, otherwise it will not run at all. So if I have to draw the speed torque characteristics of a synchronous motor, I should say this is the torque that we talk about with respect to a synchronous motor. Okay, so if I am talking about this as zero speed and this as synchronous speed, and let us say this is just a second. Let me draw it like this again. This is actually the synchronous speed. So whenever we are talking about the machine running at synchronous speed, if I'm talking about motoring action, I'm going to have this as the torque. So this is going to be the uh, electromagnetic torque that is generated. And if I'm talking about generating action, this is going to be the electromagnetic torque, that is counter torque, that is being generated by the machine. So if you try to load the machine beyond this particular torque, which is actually the maximum value of torque that can be withstood by the machine, which we called as pull-out torque. If you try to load the machine beyond this value, load the shaft beyond this value, the machine will fall out of synchronism. So abruptly the speed will come down to zero. So this is the only range in which the machine will be able to operate. This is the synchronous speed. And if you try to uh, make this work as a motor, then the maximum you can load the motor is until pull-out torque. But if you try to make this work as a generator, then in the negative side, it is going to be the same amount of pull-out torque value. So it will either run at synchronous speed or it will not run at all. So if I want to make the motor work in braking region, let us say this is actually the applied voltage, what I have applied to the synchronous machine. This is what is the synchronous reactance of the machine. And here is going to be the excitation EMF, what has been induced as the back EMF. So this is E angle minus delta. So this is the motoring action. When the motoring is taking place, this is how we are representing the synchronous machine. Now, if I want to brake, if I want to implement dynamic braking, particularly in a synchronous machine, I had to first of all disconnect this voltage. So this is actually my excitation voltage. And this is the synchronous reactance, which is excess. Now I'm going to disconnect this voltage and instead I'm going to connect a braking resistance. So I call this as RB, which is the braking resistance. This could be a variable resistance. So I can have E. Now, what is the excitation voltage or generated voltage in the synchronous machine? Because of the kinetic energy stored in the rotating parts of the machine. Now, E divided by RB plus JXS, that is going to be the current what is flowing here. So this is going to be the current that is flowing in the synchronous machine. So this is going to be IS. Now, this particular E, what is induced EMF, we said this is proportional to the frequency and flux. And of course, we have to have the excitation. So field current has to be still on. Field current cannot be switched off. So field current still exists. We are not really switching off the field supply. So field supply has to exist. But the frequency of this induced EMF depends upon at what speed the synchronous motor's rotor is running. And as the braking action is taking place, the speed will come down further and further. Speed comes down, because of which the frequency will also come down. And because the frequency comes down, the magnitude of the induced EMF will also come down. All of them will come down. So if the speed had been synchronous speed, from synchronous speed, this is going to come down. So we say that the present value of rotor speed divided by the synchronous speed is some k. This k will be less than 1 because the speed is coming down. So I can write this as k times E as the new induced EMF or continuously varying induced EMF divided by RB. And synchronous reactance is also dependent upon frequency. So I should be able to write this as KXS. That is what is IS. So I should be able to calculate this IS as, I can write this as E divided by RB divided by K plus XS multiplied by J. This is what is IS. So I can write this as E divided by RB divided by K the whole square plus XS square root of this. This is going to be IS. Now, what is dissipated in the braking resistance? I can write this as braking power. That is going to be equal to IS square multiplied by RB. So I can write this as E square divided by RB divided by K the whole square plus XS square. This is going to be IS square and this has to be multiplied by RB. So this is going to be the braking power. And this braking torque, if I want to write this as braking torque developed by a synchronous motor, which is actually braked by dynamic braking, it will be 3 times E square RB divided by K the whole square plus XS square. This has to be divided by K times omega S. Because the speed is continuously decreasing, we have to divide this by K times omega S so that we get whatever is the braking torque at present. So we would be able to adjust the braking torque value appropriately by adjusting RD value. But by implementing this, we should be able to break the machine almost until zero speed. It should not be a problem to break or incorporate dynamic braking until almost zero speed of the synchronous motor. So the next topic that I want to take up for the synchronous machine is dynamic braking. Also, we have taken a look. Now, what is the variable frequency operation of a synchronous machine? So let us try to look at variable frequency operation or speed control of a synchronous motor. So we are going to look at this. So we all know that the synchronous speed is given by 2 pi f divided by p if I am talking about radians per second, or if I am talking about RPM, it is 120 f divided by p. This is the RPM. So the frequency is going to directly decide what is the value of the speed at which the synchronous motor is running. So one of the easiest way of controlling the speed of a synchronous motor is variable frequency control. So if I use the frequency as an independent variable, what I can do is I can say what is the speed I want. So let us say omega s, what I want. If I know, I would first of all do the frequency calculation. If I know the number of poles and everything, I should be able to calculate the frequency. So what I'm getting is what is the kind of frequency at which I have to fire my inverter, which is feeding the synchronous motor drive. So I will be able to get the frequency value. Now, when I am reducing the frequency, maybe I want to run the synchronous motor at a lower speed. I can definitely reduce the frequency. But when I am reducing the frequency, what should I keep as the value of the voltage? We said that whether it is induction machine or synchronous machine or transformer, V or E is always proportional to frequency and flux, the product of frequency and flux. So if I keep the voltage at the same value, whereas reduce the frequency, we are going to have V divided by F is going to be proportional to flux. So the flux will increase tremendously if I make the frequency into half, whereas I maintain the voltage at the same value. So the machine will get into saturation, magnetic saturation, which is not a good thing at all. So if I want to maintain the flux as a constant, so when I keep flux as a constant, I have to keep V by F ratio as a constant. So same as what we did in the case of induction motor, here also I have to keep V by F ratio as a constant if I want to keep the flux as a constant. So what we are going to do is to calculate flux or voltage calculation. So I'm going to calculate the voltage. So I'm going to calculate the voltage based on flux calculation. So once I calculate the voltage, what I'm going to do is I will have actually, for most of the synchronous machines, the power supply required will be pretty large. The capacity required will be large. So what I will have is a three-phase supply, which is at 50 Hertz. And I will normally have a rectifier sitting here. So this rectifier will be fed with three-phase supply. And this rectifier will be a controlled rectifier also. This will be a controlled rectifier. So from the calculated voltage value, what we will do is to calculate the firing angle alpha. So this will actually be fed to a firing circuit. The firing circuit will have this alpha value, and this alpha will be given to the controlled rectifier, and the controlled rectifier output will be given to a voltage source inverter. So the voltage will be controlled. The magnitude of the voltage will be controlled by the controlled rectifier, whereas the frequency will be controlled by a voltage source inverter. And the voltage source inverter output is going to be given to the synchronous motor drive here. So in true synchronous mode of operation, this we call as true synchronous mode. So in true synchronous mode of operation, frequency will be an independent variable which will be fed to the inverter, and the inverter will be able to take care of what is the kind of frequency we are injecting to the synchronous motor drive so that the speed that we require is reached appropriately. The magnitude of the voltage will be maintained in such a manner that voltage and frequency are proportional to each other. If I talk about 50 hertz and I'm going to have the voltage to be, let us say, 1000 volts. If I am talking about 10 hertz, I should have only 200 volts applied. So voltage and frequency should be proportional to each other, and correspondingly, the voltage will be adjusted by adjusting the firing angle to a controlled rectifier. The controlled rectifier output will be fed to the voltage source inverter, and the output of the inverter will be fed to the synchronous motor. So if I want starting of a synchronous motor using a voltage source inverter, I'll first start with maybe zero point 0.1 hertz. Corresponding to 0 0.1 hertz, I may have only 10 volts applied. I might have to again compensate for the stator drop like what I did in the case of induction motor. So I might compensate for the stator drop. So 10 volts plus whatever is IS times RS plus JXS. This has to be added. Then from 0 0.1 hertz, I may next go to 0.5 hertz. So at 0.1 hertz, slowly the rotor will catch up with the stator revolving magnetic field. There will be hunting oscillations, and ultimately it will settle down at a speed corresponding to 0 0.1 hertz. Then I'll go to 0.2, 0.3, 0.4, and so on, and then slowly increase very, very slowly the frequency, and correspondingly have the hunting oscillation happening at every step, and then it is going to synchronize with the revolving magnetic field, and it is going to go further and further. So from 0.5 hertz, I'm going to again increase it to 1 hertz, 2 hertz, and so on. And slowly it will go step by step to 50 hertz. The voltage will also start from the minimal value of 5 volts or something. It will go slowly to 10 volts, 15 volts, 100 volts, and so on until 1 kilovolt. So the starting will be done by slowly varying the frequency and correspondingly the voltage, and it will go from 0.1 to 1 hertz to 2 hertz to 10 hertz to 15 hertz to 50 hertz finally, and the voltage will also be increasing slowly, and this is what happens in true synchronous mode. And if we want to have speed greater than the rated speed. So whenever we want to have speeds greater than rated speed, in those cases, we have to freeze the voltage. V is frozen. at rated value. Only the frequency will be increased. And because of the increase in the frequency, the speed will increase all right, but V divided by F, which is actually deciding the flux will become lower. So we are going to have flux is lower. So the torque producing capability will also decrease. We will not be able to produce as much torque as what we were producing until rated speed. So the true synchronous mode adopts voltage and frequency increased proportionately until rated speed. But whenever we are talking about speeds greater than rated speed, that is actually going to have the voltage frozen at rated value, flux will be lowered, so the torque capability of the machine will also be lowered. We will work out one numerical example on true synchronous mode or variable frequency operation of the synchronous motor in the next class. And after that, we are going to look at another way of controlling the synchronous motor drive, which is known as self-controlled synchronous motor drive or self-control mode of the synchronous motor drive. So in the next lecture, we'll be working out one problem on variable frequency operation of the synchronous motor. And after that, we look at the self-controlled mode of synchronous motor drive.